Hi, and welcome to the second video in a series about differential forms. In the last video, we looked at this idea of a tensor and the set of all k-tensors forming a vector space over a given V. This is perhaps the fundamental result that we will pursue in this exploration of multilinear algebra, so-called, and we will continue to show results and eventually build into the tensor product, the wedge product, and eventually integrating over such things. So last time we showed, as I have in quite a lot of space here, shown that L to the k of V, the set of all k-tensors over V, is in fact a vector space under associated operations of sums of tensors and scalar products of some real number times a given k-tensor. So what we're going to do here kind of appeals to an analog of just linear transformations in general. So a very powerful idea in linear algebra is that one can completely characterize a linear transformation between vector spaces by determining how it evaluates on basis elements. So this is what we want to show for multilinear transformations in an appropriate manner, that we can entirely determine the nature of a multilinear transformation as defined above on basis elements. By the way, it acts on basis elements. So let's just show this as a lemma. So we let let A1, I'm going to use these set brackets, although that's not always how it's written. Let A1 through AN be a basis for V. If we have f and g, these two k-tensors from V to the k to r, are k-tensors in L to the k of V, and if f of what I will write here is I sub 1 through I sub k, which I will explain in a moment, equals g of I sub 1 through I sub k for every k-tuple, big I equals I1 through I sub k from the set 1 through n, which will also just start denoting by sometimes this shorthand notation is used. Then we claim that f simply equals g. So what is this stating? It's analogous to what I described earlier as determining linear transformations based on how they operate on bases. And if we have this let's say a sub I basis here, and if we have this k-tensor acting on every k-tuple of basis elements possible, so you're taking k from n of these, and if f and k act the same way on each k-tuple of basis elements, then we claim that they are in fact the same thing. They're equivalent, they're equal as k-tensors. So how do we prove this? And actually, one important requirement that I should have pointed out really is that this k-tuple definition here does not presuppose anything about the ordering or the arrangement of these indices. So it doesn't require that such indices, a sub 1 through a sub k, it just matters that they agree on all k-tuples here, right? So let's prove this. Given an arbitrary k-tuple of vectors of V, or equivalently elements of v to the k, we can express each individual vector in the form of a linear combination of its basis elements. Just fundamental idea. Express each v sub I in terms of the a sub i's, where we state the sum here. Let's say j equals 1, since we're using the other index I already. So I to n for the dimension, and we have c ij times a to the a sub j, right? Just linear combinations of basis elements will yield every vector, and hence, taking these for every slot of k-tuples, we just get expressions of these k-tuples in each slot as linear combinations of basis vectors, right? Then we have f of v1 through vk, which equals this sum here, which is going to look a little bit convoluted at first maybe. So j1 equals 1. This is our index. We run through n as above. c1 j sub 1, and then a j sub 1, sorry, f of a j sub 1, v2, and then through vk. Right? So now over here, this sum is basically stating we're examining this first element here, so v1, and we are writing it as this sum over here, just individually. And there's nothing special about it just being the first one, because as we'll just write here and kind of just explicitly show for v1 and then v2, and then just sort of say so on, we can write as a double sum for j1 and j2, j2 equals 1. I don't want to run out of space here, so through n of c1, j1, c1, j1. This is supposed to be this subscript here, and I should have written it more clearly here, so I'll just erase it actually, because, so c1, j1, because this is the j equals 1 case for v1, c2, and then j2, so 2 and then j2 for that case, and then times f of a j1, a j2, v3, onwards to vk. And this just equals now j1 equals 1. This is not really good notation either again, but jn, sorry, it'll go jk equals 1 through n. And now we have c1, j1. We have c, sorry, I don't want to mess up these indices because there's so many going on right now. You're going from j1 equals 1 to j1 equals n. So you have c1, j1. And yes, you will go from jk equals 1 to n. So c, k, jk. And then you will have expressed f a j1 through a jk as just these basis elements, right? Okay, so this is our full expression here, and we can condense it as just v1 through vk equals just this overall sum, where 1 is less than or equal to j sub 1 through j sub k is less than or equal to n. And then this is over the scalar product first, c1, j1, to ck, jk for both of those indices, and then f, how it acts on these basis elements. So a, j1, a, jk, close parentheses. All right, so quite a large sum going on here, or quite a long sum. And we will just conclude by simply stating which holds as a computation for the k-tensor G. Hence, if f and g agree on all k-tuples of basis elements, on all k-tuples of vectors first, we have shown they agree on all k-tuples of basis elements, so equivalent formulation. K-tuples of vectors they agree, I want this to be legible, sorry, on all k-tuples of basis elements. Okay, so that's our result here. And now we will show another result that is analogous to linear transformations and how we specify them based on their values on basis elements from, let's say, from a space V to W on V. We can define how a k-tensor is, or we can specify a k-tensor based on its values on arbitrary k-tuples of basis elements. So that is a consequence of what we're going to show now as a theorem. So let V be a vector space with basis A1 through AN, or I'll just say, let V have basis A1 through AN. So then we let, as above, I equals I sub k, so I sub 1 through I sub k. Let this be a k-tuple of indices from the index set. The set which we denoted as bracket n, or just all the integers from 1 through n, right? So it's a k-tuple of indices. Then we claim there is a unique k-tensor which will denote phi sub I on V, such that for every k-tuple, which we'll denote by J, which consists of these indices J1 through Jk, let's say, from index set n, and now we specify how it acts. So phi sub I of a J1 through a sub J sub k is going to basically be the Kronecker delta product just on this big I and big J. Basically, if across I and across J, all these indices match. So 0 if I does not equal J, so not all the indices are like that. And then 1. So this this unique k-tensor, which gives 1 if I equals J. And just like how one might construct the dual basis for the dual space, this is kind of a generalization of how the space of all k-tensors L to the k of v is kind of like that generalization we saw of the dual space, right? And of course, our final claim, these tensors phi sub I form a basis for L to the k of v. So how do we prove this? And actually, I should just write, are called, as I referenced earlier, I think, they're called the elementary k-tensors, because elementary referring to kind of like basis elements, or just constructing the space from these fundamental k-tensors. The elementary k-tensors on a given space V. Which corresponds to a certain basis, but that's implicit. Okay. Let's just prove this. Uniqueness we have already shown, as a matter of fact. And why, you might ask, have we shown uniqueness? And we have exactly shown why, if this exists, it will be unique by the preceding lemma. So if we have any two k-tensors that agree like this, then we know they're the same. So that is the uniqueness property, except we're just specifying it like this, and if they share this property, they must be equal. So that is uniqueness of this given k-tensor phi sub I for each set of indexes, or k-tuple of indices. Let's show existence. Existence of these phi sub i's. So consider first the case I equals 1, which we know to be the dual space. Then we have seen the construction of a dual space, or hopefully you have prior in a linear algebra course. We can define the construction of this dual basis, which I alluded to earlier, can be constructed can be determined by specifying its values in arbitrary basis elements. Right, so we define phi I of aj as just delta ij, or in other words, 0 if these indices do not match, 1 if they do. And this is how we construct the space of linear functionals. In the cases k, or I'll just say case because we're treating all of them as 1. In the case k is greater than 1, so now we're looking at more than just the dual space. Define phi I by, instead of now looking at phi I in k equals 1, because you just had one index to examine like this. In k, you have k tuples, so you have to examine k elements in this set, whereas you just had one here just as a single index, right? You define it like this. So phi sub I on v1 through vk of vectors equals this product over here, where phi I1 of v1, maybe I should write this with product notation. That'll be a lot easier than just writing it exhaustively, I think. So let's just write this product. I equals 1 to k, where we have phi I1. Never mind, I'm not going to use the index I here. We have, let's say, j equals 1. Yes. So phi sub I sub 1, or no, sorry. Phi sub I sub j of v sub j. Yes, this is what we want. Where this will be phi I1 of v1 times phi I2 of v2, so on and so forth till phi ik of vk for these vectors here. And we can check these two facts. Each phi I is linear. From preceding facts. So each phi I is linear, and that multiplication is distributive, right? Sorry. Conclude that phi I, in fact, is multilinear. Okay, so we have individual linearity, we have distribution over multiplication, so now we have the product of linear things across this distributive operation that is multilinear by definition now. So this has the desired values on our basis elements, or our tuples, a sub j1 through a sub jk, which can be checked. And now we will show these VI's form a basis, sorry. Of L to the K of V, sorry. Let F be an element, let F be an element of L to the K of V. That is, it is a k-tensor. And show it can be expressed as a unique linear combination of these phi i's. Okay, how do we do this? For each k-tuple I sub 1 through I sub k, F is going to act on it in a well-defined manner. So we can define a scalar that F maps for each k-tuple of basis elements according to this index set I. So for each, k-tuple I equals I sub 1 through I sub k, define the scalar d sub I equals how F acts on the corresponding basis elements indexed by the set I. Hence, a I sub 1 through a I sub k. So each of these d sub i's are going to be defined in this manner. So consider now this k-tensor which we'll call G, and it equals the sum over this J, which J is going to have a similar role as above, d sub J times v sub J across all k-tuples J J1 through Jn. Sorry, so Jk, conflated k and n. K-tuples J from n. So this indexing set. then the value of g on this k-tuple, which we have ai sub 1 through ai sub k, on the k-tuple of the basis elements that correspond to the indices I, so ai sub 1, ai sub k, is equal, to d sub I, the scalar that we defined above, by the preceding theorem. And I will scroll up to it in a moment. Preceding theorem. Okay, and the one that we want to really look at is this construction of the agreement, similar to how we specified the dual for these indices singularly. It is this construction over here that we have to be equal to g. So how it acts now on these basis elements is going to just be 1 in accordance with this index set I being equal to j of k-tuples. Hence, if you take the summation over g, which is equal to the scalars of all d sub j times phi sub j, we have this phi sub j is only going to be equal to 1 times the scalar if I equals j and 0 otherwise. So taking the sum over all of those indices where I and j differ is just going to yield 0, and hence they are vacuous in the sum. But if we take the ones where I and j are equal, we simply get just the scalar d sub I. So that's just by this equation over here. The same is true by construction for f actually, because f is unambiguous because we defined f just up here. By our uniqueness lemma, we showed that f and g agree in this sufficient manner. Hence, f is going to be equal to g. And this is unique because of our lemma, and we have shown now that f equals g, and this representation is in fact valid. Okay, so really, I think this is where we will end this video, and essentially I'll summarize what we've done here, which is to show that this kind of representation, that if we have given scalars for what we defined as d sub I for each index set I, each k-tuple, if we are given these scalars, there is exactly one corresponding k-tensor, which we had f here, such that f evaluated on the corresponding indices of I are going to evaluate to d. So this is a unique representation that exists for each one. And a k-tensor, essentially, may be defined by specifying its values on arbitrary k-tuples of these basis elements, a sub I sub k. Okay, so this has been quite a lot of machinery going on, but hopefully it is clear. And in the next video, we'll just go through a quick example, and I'll keep that relatively short because I know this is around half an hour now as of recording. And in the video directly subsequent to that, we will look at the tensor product. Very exciting. I know I've said that a lot, but thank you for watching, and see you in the next video.